Welcome everyone at part 4, lateral control using symbolic modeling. I've decided to split our videos into small videos instead one long one, and we would start with the theoretical introduction about lateral control, which is 4.1. And also in 4.1, we will have the mathematical modeling of one of the techniques for lateral control, which is called pure pursuit lateral control. In 4.2, we'll set up the Unreal environment that suits with the lateral control. And we would also add the Tesla Cybertruck model. In 4.3, we would add the vehicle path splines, which is basically that usually is coming from the motion planning, as we'll see later, and that defines the path that the vehicle should or must follow. In 4.4, we would see the implementation of pure pursuit using Unreal Game Engine or within Unreal Game Engine. 4.5 would be the mathematical modeling of Stanley lateral control, which is another geometric technique beside the pure pursuit. And then 4.6 would be the implementation of Stanley lateral control. Now, next, basically, which is 5, would come to the lateral control using machine learning and mainly reinforcement learning. In part 4, we are covering the symbolic way of doing or symbolic modeling of lateral control. So in lateral control, we have different methods or different techniques, starting with geometric methods, or which they are actually under symbolic systems. We have two techniques, which is the pure pursuit, which is kind of classical traditional sample model, and also Stanley. Both these techniques, basically, they were used or implemented in the early DARPA self-driving car challenges. More advanced lateral control can be done using MPC or model predictive control, which is also symbolic modeling. MPC requires basically the mathematical model of the plant or actually of the car, which means giving, for example, the steering angle, how would the car respond to that steering angle, or, for example, also can be applied to the longitudinal or the cruise control, which is basically you need also the model, the plant model that takes the throttle angle as an input and predict the speed. So we basically this is what is MPC, and MPC, as I said, requires the mathematical model of the plant, which is also symbolic. And of course, there is the machine learning based, which is mainly using reinforcement learning control systems. So in part 4, as I said, we will cover symbolic models, and we mainly will focus on the geometric method. I will not cover model predictive control in these tutorials because we don't actually have the mathematical model or the plant model of the car. So we'll deal with it as a black box. And for that, we have two options, either the geometrical method or the reinforcement learning method, which would be in part 4. So we will start with geometric lateral control. But before that, we need to know, what are we controlling? Let us assume that you need your self-driving car to take you from home to work. Now, first thing this car needs is basically the route that is coming from your navigator that's using GPS. And this is the macroscopic route. And as I said, it's connecting your home to work. Now, there is the microscopic route planning, which basically would first use the perception of your car, which is using cameras, lidar, and other sensors, and the state estimation localization of your car system that we will see later in this tutorial. Using that, it will start to first, for example, decide which lanes it should take. For example, if we are driving in most Europe except UK and US, for example, then the car should be on the right side of the route or the road. And basically, of course, this car needs to stop at traffic lights. This car needs to avoid obstacles. If, for example, if you want to take over, this also car needs to plan the route of taking over or the path of taking over. So this is the microscopic, of course, which is more complicated than macroscopic, but usually we need both of them to know how to get to the final destination. What we see here kind of are an example of microscopic planning. So we have this control point, which are in the which are presented in brown points here. And these are the control points, and we have the interpolation of this point, which is we have here, for example, linear interpolation that is in black lines. Of course, the linear interpolation is not optimum. We usually use splines or cubic interpolations because they make the movement of the vehicle more smooth and more comfortable and more stable as well. So we need to basically have the path that is coming from motion planning, as I said, that combines the macroscopic and microscopic planning. And then we need to control or we need to do both actually, the longitudinal control and the lateral control of the vehicle, which is a steering control, in order to follow that path. So lateral control is about path tracking or path following. What is called the bicycle kinematics model is used widely in self-driving cars. And from its name, it's coming from bikes or the bicycles, and the kinematics here basically is the study of motion, if you don't know this term. And what we need to do is, first of all, is basically to generalize the bicycle model to use it on vehicles. And to do that, we have the following assumption. First of all, that the front wheels, they are always the right and left wheels, front wheels, they are always parallel and they have the exact orientation. If we have so, we can represent both of them in one front wheel, sorry. And with the same case for the rear wheels here, that they have always the same orientation, that we can represent them in one rear wheel. And if we do so, we can have like a bicycle model, as I said, that has only two wheels. Now, what we want to do with lateral control, and how can we use this bicycle model for that? We need to calculate the steering angle of the front wheel. This steering angle basically that would lead our car to converge at the target path, as we will see here, which is, as I said, it's combination of basically the macroscopic and microscopic path. So first of all, what we need to consider here some parameters, and we will apply some geometric laws here to get that steering angle. So first of all, we need to know the distance between the two wheels, and which is here described by or represented by L. And what we need to actually find what is called the look ahead vector. The look ahead vector is basically centered at the rear wheel. And so this is basically the center or the starting of the look ahead vector, and ends up at the target point, which is located at the path, the target path that we want, as I said, the vehicle to converge at. Now, this target point, how to find it? There are two approaches. First, we fix that LD length, or as you'll see later, we can actually model it as a function of the speed of the vehicle. And then we search along this path. If we actually estimate the mathematical model of that path, we'll see also that later, we can search along that path for all the points that they have the LD distance from the reference point here. Then we select the point that is, let's say, ahead of the vehicle. So that, for example, it has a length LD, and it's ahead of the vehicle, which means it's actually located after the front wheels. This is the first approach. The second approach, basically, we search for the point that is closest to a reference point, let's say here, which we'll use that in our modeling, which is actually located at the major axis here, but located, let's say, in the front of the vehicle. We select the closest point at the target path to that reference point here, and we consider that as the target point. Now, having the target point and having the reference point here, we'd have this look ahead vector, which has the length of LD. We have the enclosing angle between that look ahead vector and the major axis here, which is called alpha, which is also important in our modeling. So using these dimensions and using what is called the instantaneous center of rotation, which is known in physics, with this car would actually follow this curve until it reaches our path, then it will converge at that path. So this curve has this instantaneous center here. It has basically the radius of r, And these are two radius basically with the LD, they form here a triangle as we see there, which could be derived that this is the 2 alpha and this is the alpha, as you remember. And basically, first of all, if we have this instantaneous rotation, then the curvature of that curve is given by 1 over r, which is the radius of that rotation. Now, using trigonometric laws, we can know that the LD over the sine of alpha is equal to 2r. And then, for example, if we know that the curvature is 1 over r, then the curvature would be equal to 2 sine alpha over LD. Okay, so just remember first of that, because we need to know the curvature of that path. And if we know that curvature, we can actually directly derive the angle or the steering angle of that bicycle model. So if this is our steering angle here, which is delta, giving it basically the kappa here, which is our curvature from the bicycle model, for the bicycle kinematic model that you can look for it, is actually that steering angle is equal to the arctan of the kappa, which is the curvature, multiplied by L, which is our here, the distance between the rear and the front wheels. Now we know that the curvature is equal to 2 sine alpha over LD, or actually it's equal, sorry, to the 2 sine alpha over LD. So we have L here. So the model of pure process control would be now 2L multiplied by sine alpha over LD. And that's it basically what is the basics of pure process controller. We will see later in the modeling in Unreal that if we actually make the speed or the distance here as a function of the speed, then it will be more accurate. So in this way, we control the steering and also we control the speed or the longitudinal control as well using pure pursuit controller. So before I move to the modeling, the Unreal modeling, this is basically how we calculate our steering angles. We need only to know the target point. We need to find the target point. We need to know path. We need to actually calculate the alpha here. Then the L is known, and we need to calculate the LD. Then we can get the steering angle.